Lie algebras, problem session 3, semi-simple algebras. Problem 1. Let G be a non-zero finite-dimensional Lie algebra over the complex numbers, such that the category of finite-dimensional G modules is semi-simple. Prove that the algebra G itself is semi-simple. Solution. Consider the adjoint representation of G. So each element of G acts as a linear operator on G, given by bracketing with this element on the left. Due to our assumptions, this representation is semi-simple, because it's finite dimensional. So we can write the algebra G as a direct sum of simple representations under this adjoint action. So you write G is equal to G1, direct sum with G2, direct sum with so on, direct sum with Gk. And note that each Gi is an ideal because it is a submodule of the adjoint module. Consequently, if we bracket Gi and Gj for different I and j, we must get 0, because each of them is the ideal. So this bracket belongs to the intersection of Gi and Gj, and this intersection is 0 if I is different from j. Now let us fix some Gi and let us investigate this Gi in more detail. By assumption, this Gi is simple when considered as the adjoint G module. Moreover, we know that the bracket of Gi with any different Gj, so any other Gj, where j is different from I, is 0. Therefore, it follows that the Gi is also simple as the adjoint Gi module. Let us first assume that the bracket of Gi and Gi is 0. We already know that the bracket of Gi with any other Gj is 0, so it follows that Gi is an abelian direct summand of G. Since it is a direct summand, the category of finite-dimensional modules over Gi is of course a full subcategory of the category of finite-dimensional G modules. Further, since Gi is abelian, the universal enveloping algebra of Gi is just the polynomial algebra in a finite number of variables. The number of variables is the dimension of Gi. And the category of finite-dimensional modules over a polynomial algebra in a finite number of variables is not semi-simple. Indeed, to construct some non-semi-simple module, we can take any non-zero finite-dimensional vector space of dimension greater than 1 and make all variables act on it as the same non-trivial Jordan cell. So if the Jordan cell is non-trivial, the representation is not simple and is not semi-simple, and of course all variables commute because they all act as the same linear operator. So it's easy to construct a non-semi-simple module over the polynomial algebra. Therefore, our assumption that the bracket of Gi with itself is 0 leads to a contradiction. Hence, the bracket of Gi with itself is non-zero, which means that Gi is a non-abelian Lie algebra. Since the bracket of Gi with itself is a submodule of Gi, from the simplicity of Gi, due to our assumptions, we obtain that the bracket of Gi with itself is actually equal to Gi. And this directly implies that Gi is not solvable, and hence it is different from the radical of Gi. Now let us look at the radical of Gi. So the radical of Gi is an ideal of Gi. In particular, it's a submodule of the adjoint module. But by our assumption, the adjoint module is simple, so it only has two submodules, Gi and 0. And we just said that the radical of Gi is not equal to Gi. Therefore, it must be 0. And if the radical of Gi is 0, this means that Gi is a semi-simple Lie algebra. Well, since we assumed that the adjoint action of Gi on itself is a simple module, it follows that Gi is actually a simple Lie algebra. And so our algebra G, which is a direct sum of simple Lie algebras Gi, is semi-simple. And this completes problem 1. Problem 2. Compute the Casimir element for the Lie algebra SL3 and evaluate it on the natural SL3 module C3. Solution. Recall that the Casimir element C for a semi-simple Lie algebra G is defined as the sum xi times yi, where xi and yi are two bases in G that are dual with respect to the Killing form. So we will construct the Casimir element using this definition. Let Eij be the usual matrix units. Then we can take as the first basis xi, the standard basis of SL3, which is given by the following elements. So first we have the matrix units E12, E23, E13, E21, E32, E31, and then we have two diagonal elements, E11 minus E22 and E22 minus E33. Okay, so the really interesting part of this problem is to compute the basis yi. Recall also that we have the following property of the Killing form. With respect to the Killing form, two root subspaces G alpha and G beta are orthogonal unless alpha is equal to minus beta. This means in particular that in the case when our xi is equal to, say, the matrix unit E12, the corresponding yi must be the matrix unit E21 up to some non-zero scalar. And similarly for all other matrix units which are involved in our basis. So let us first find the non-zero scalars which appear for those summands in the Casimir element. Okay, for this we need to take a look at the matrices of the adjoint operators for the elements E12 and E21. So the adjoint element for E12 does the following. So E12 bracket with E12 is of course 0. Therefore, the first column of the matrix is 0. E12 bracket with E23 gives E13. So the second column in the corresponding matrix is 0, 0, 1, and the rest is 0. Next, the bracket of E12 and E13 is 0. So the third column of the matrix is 0. The bracket of E12 and E21 is actually E11 minus E22, which means that the fourth column of our matrix has all zeros apart from 1 at position 7. Next, the bracket of E12 with E32 gives us 0. And the bracket of E12 with E31 gives us minus the element E32. And then the bracket of E12 with E11 minus E22 gives us minus 2 times E12. So the next column is minus 2 and then the rest is 0. And the bracket of E12 with the Cartan element E22 minus E33 gives us E12. So the last column is 1 and then the rest is 0. And similarly, we compute that the matrix of the adjoint operator for E21 is as follows. So the first column is all zeros but minus 1 at the 7th position. The second column is 0. The third column has 1 in row 2. The rest is 0. Column 4 is 0. Column 5 has minus 1 in row 6. The rest is 0. Column 6 is 0. Column 7 has 2 in the fourth row, and the rest is 0. And the last column has minus 1 in the fourth row, and the rest is 0. If we multiply these matrices and compute the trace, then this minus 2 will hit minus 1. Then this one will hit this one. This minus 1 will hit this minus 1. And this 1 will hit this 2. So adding all this up, we get 6. which means that the corresponding summand in the Casimir element is 1 divided by 6 times E12 times E21. And similarly, we obtain the corresponding summands 1 divided by 6, E13 times E31, E23 times E32, and so on. So we have 6 summands, where at each of them the coefficient is 1 divided by 6. It remains to consider the Cartan part of the Killing form. So in the Cartan subalgebra, we have two basis elements, E11 minus E22 and E22 minus E33. Their action on the D algebra is diagonalizable, and our standard basis consists of eigenvectors. So E11 minus E22 has the corresponding eigenvalues on our basis elements 2, minus 1, 1, minus 2, 1, minus 1, and then 0 and 0. And E22 minus E33 has the following eigenvalues, minus 1, 2, 1, 1, minus 2, minus 1, 0, 0. So let us record these non-zero parts as vectors A. So 2 minus 1, 1, minus 2, 1, minus 1. That's the diagonal vector corresponding to E11 minus E22. And the vector B, minus 1, 2, 1, 1 minus 2 minus 1. That's the diagonal part corresponding to E22 minus E33. This is the only essential thing which we need to compute the coefficients. So now we want to determine the dual basis consisting of the diagonal matrices with the corresponding diagonal parts, which we don't know, so we denote them by A tilde and B tilde. So what do we know about A tilde and B tilde? So they belong to the Cartan, so each of them is a linear combination of A and B with some coefficients. So let's write A tilde as XA plus YB, and then B tilde as UA plus VB. We need to determine X, Y, U, and B. What are the conditions for A tilde and B tilde? So this should be a dual basis with respect to the Killing form. So if we take the Killing form between A and A tilde, we should get 1. And if we take the Killing form between B and A tilde, we should get 0. If we take the Killing form between A and B tilde, we should get 0. And the Killing form between B and B tilde gives us 1. So how to compute the Killing form? The Killing form is a trace of the product of the corresponding matrices. For diagonal matrices, the product just gives the product of the corresponding diagonal element. So we have A, which has 2 minus 1, 1 minus 2, 1 minus 1. And then A tilde has XA plus YB. So A tilde has coefficients 2x minus y. That's the first entry. Minus x plus 2y. That's the second entry, and so on. So we take this vector, XA plus YB, and we take the scalar product between this vector and the vector A. That's exactly the Killing form between A and A tilde. We write the corresponding equation, and we get 2 times 2x minus y minus x plus 2y plus x plus y minus 2 times minus 2x plus y plus x minus 2y and minus x minus y. This should be equal to 1. Similarly, the scalar product between the vector b and the vector A tilde gives us this expression, and this should be equal to 0. Similarly, the scalar product between B tilde and A gives us this expression, and this should be equal to 0. And finally, the scalar product between B tilde and B gives us this expression, and this should be equal to 1. Now we can simplify the left-hand side in all four equations, and so we will get the following system of linear equations. So the first equation gives us 12x minus 6y is equal to 1. The second equation, minus 6x plus 12y is equal to 0. The third equation gives us 12u minus 6v is equal to 0. And the last equation, minus 6u plus 12v, is equal to 1. So this system of linear equations has a unique solution, namely x is equal to v is equal to 1 divided by 9, and y is equal to u and is equal to 1 divided by 18. So this gives us the following summons. So we take our element e1 minus e22, and we should multiply it with a tilde, which is 1 divided by 9 times e11 minus e22 plus 1 divided by 18, e22 minus e33. So that's the summand for the first Cartan element, and for the second Cartan element e22 minus e33, we should multiply it with b tilde, which is 1 divided by 18, e11 minus e22, plus 1 divided by 9, e22 minus e33. So now we can add up all our summands which we got, and we have the following expression for the Casimir element. 1 divided by 9, e11 minus e22 squared, plus 1 divided by 9, e22 minus e33 squared, plus 1 divided by 9, e11 minus e22 times e22 minus e33, and then plus 1 divided by 6, and then the big sum, e12 e21 plus e13 e31 plus e23 e32 plus e21 e12 plus e31 e13 plus e32 e23. This is the Casimir element for SL3. Now we need to evaluate this Casimir element at the natural SL3 module C3. This module is obviously simple, and so the Casimir element acts on it as some scalar. So we need to determine the scalar, and for this we can just apply the element at any vector and see what happens. So we take the first basis vector e1 and apply our expression to e1. Which summands here do not annihilate e1? Those where we have something with 1 on the right. So that's the summons 1 divided by 6 e12 e21, 1 divided by 6 e13 e31, and 1 divided by 9 e11 squared from this bracket. The rest annihilates e11, so it contributes with 0. So adding up the coefficients, 1 divided by 6 plus 1 divided by 6 plus 1 divided by 9, we get the coefficient 4 divided by 9. And that's exactly the answer to our problem. So this is the scalar with which our Casimir element C acts on the natural SL3 module. This completes problem 2. Problem 3. Let phi be the root system of a semi-simple Lie algebra G with a fixed Cartan subalgebra H. Let alpha and beta be two roots, that is, two elements in phi. First, prove that the bracket of G alpha and G beta is equal to 0, provided that the sum of alpha and beta does not belong to phi, and also alpha is different from minus beta. 2. Prove that the bracket of G alpha and G beta is equal to G alpha plus beta, provided that alpha plus beta belongs to phi. And 3. Prove that the bracket of G alpha with the bracket of G alpha with the bracket of G alpha with the bracket of G alpha and G beta is equal to 0. Solution. We know that the bracket of G alpha and G beta is a subspace of G alpha plus beta. Recall that G gamma is not 0 if and only if gamma is 0 or gamma is an element in phi. Therefore, in the case when alpha plus beta is not in phi and alpha is different from minus beta, then G alpha plus beta is 0, which implies that the bracket of G alpha and G beta is 0. Now let us prove the second claim. Assume that alpha plus beta is an element in phi. Then the elements alpha, beta, and alpha plus beta, they all belong to phi. In particular, Since the only scalar multiples of alpha which are in phi are plus and minus alpha, it follows that alpha is not a scalar multiple of beta. Let us denote by G of alpha the SL2 subalgebra of G, which is given by the subspaces G alpha, G minus alpha, and their bracket. Let V be the direct sum of all G gamma, where gamma is of the form beta plus K alpha, where K is an integer. Then, of course, V is a finite-dimensional G of alpha module. Recall also that each G gamma, where gamma is in phi, is a one-dimensional space. Since alpha is not a scalar multiple of beta, it follows that all G gamma appearing in V have dimension 1. Now recall the classification of simple finite-dimensional SL2 modules. The simple finite-dimensional SL2 modules are L of n, where n is a non-negative integer. The module L of n has the following properties. The Cartan element H acts diagonalizably on L of n with simple spectrum. And the spectrum is equal to n minus 2, n minus 4, and then all the way down to minus n. Furthermore, the element E sends Ln sub I, so the weight space of Ln, which corresponds to the weight I, to Ln sub I plus 2. And the kernel of E on the module Ln is exactly the highest weight Ln sub n. And the action of the element I between Ln sub I and Ln sub I plus 2 is bijective, provided that I is in the spectrum and is not equal to n. Next, let us observe that all non-zero H-weight spaces in our SL2 module V differ by construction by integer multiples of alpha. So this means that when we write the semi-simple module V as a direct sum of simple modules, the only modules which will be involved in this direct sum are the modules Ln, where all involved n are either odd or they all are even. So all n's which are involved should have the same parity. And then, if we look at such direct sums, we can observe that if we have a direct sum of Ln's with even n, then the number of summons is the dimension of the zero weight space. And if we have a direct sum of Ln's with odd n's, then the number of summons is a dimension of the weight space for the weight 1. And since we know that all weight spaces in our module V have dimension 1, it follows that our module V is, in fact, simple. And in any simple module, the action of G alpha between two non-zero weight spaces is bijective. So this means that the bracket of G alpha and G beta is actually equal to G alpha plus beta, in the case when alpha, beta, and alpha plus beta are all elements in phi. It remains to show the last claim that starting from G beta and taking 4 times the bracket with G alpha, we necessarily get 0. From the previous claims, it is enough to show that beta plus 4 alpha is not equal to 0, and beta plus 4 alpha does not belong to phi for all alpha beta in phi. If beta plus 4 alpha is 0, then alpha is a scalar multiple of beta. But the only scalar multiples of beta in phi are plus and minus beta. However, beta plus for beta is not 0, and beta minus for beta is not 0. So here we get a contradiction. So it remains to show that beta plus for alpha is not an element in phi for all alpha and beta in phi. If alpha is a scalar multiple of beta, then beta is alpha or minus alpha. If beta is alpha, then beta plus 4 alpha is 5 alpha, which is not in phi. If beta is minus alpha, then beta plus 4 alpha is 3 alpha, which is again not in phi. And if beta is not equal to plus or minus alpha, so if they are not scalar multiples of each other, then the intersection of the linear span of alpha and beta with phi is a root system, or root subsystem of phi of rank 2. And we know all root systems of rank 2. So these are the root systems A1 times A1, A2, B2, and G2. So this is just a finite set of root systems, and so we have finite set of pairs alpha, beta in these root systems, and we can easily check by a direct computation that for all choices of alpha and beta inside root system of rank 2, the element beta plus for alpha will not be an element in the root system. And this completes problem 3. Problem 4. Consider SL3 as a Lie subalgebra of SL4 embedded into the top left corner. So we have 4 times 4 matrices with trace 0, that's our SL4, and inside we take the 3 times 3 matrices in the top left corner, also with trace 0. That's our SL3. Determine the decomposition of the corresponding adjoint module, that is the adjoint action of SL3 on SL4, into a direct sum of simple SL3 modules. Solution. Let us denote by A the SL3 subalgebra of SL4 given in the formulation of our problem. Let us denote by V1 the vector space inside SL4 given by all matrices of the following form. So we have zeros almost everywhere, apart from the first 3 entries in the last column. Denote by V2 the vector subspace of SL4 given by all matrices of the following form. We have zeros everywhere, apart from the first 3 entries in the last row. And denote by V3 the linear span inside SL4 of the following diagonal matrix: 1, 1, 1, minus 3. Note that this matrix is a very special matrix. It has trace 0, so it belongs to SL4, but it also commutes with all elements in SL3, because in this top left corner we have the identity matrix. It is easy to check that all subspaces A, V1, V2, and V3 are adjoint SL3 submodules. This should be SL3. So they are stable under the adjoint action of SL3. Of course, A is SL3 itself, so it's obviously stable under the adjoint action. And then from how V1 looks like, it's clear that this is just the defining SL3 module C3. And then V2 is some kind of dual to this module. And V3, this matrix commutes with SL3, so of course it gives us an SL3 module. Next, all these 4 modules are simple. So A is SL3. SL3 is a simple Lie algebra, so it's simple as a module over itself. V1 and V2 come from the natural module, which is simple, and V3 has dimension 1. So all these are simple. Of course, their sum is direct, and they add up to the algebra SL4. So considered as an adjoint SL3 module, SL4 decomposes into the direct sum of A, V1, V2, and V3. Thank you very much, and that completes the problem sessions for this course.